go ahead and just say yes in the chat, because I can't, my phone's being used for recording or for streaming. Someone will need to go ahead and just type it in the box, or maybe I can actually add you guys to the stream as guests. Let's see if that works. Okay. Okay. If anyone's joined, say hi. Okay, just check. Because in any case, I can simply just get started. Okay, cool. You got set up. Thank you, my man. All right, anybody else? Hey, Uday. How's it going? All right, you know what? Let me just try and see if I can actually add you guys as guests. I don't know how long that's going to take, but let me just try. What do we do? Okay. How's the audio quality? Is it good? How's the audio? Okay. All right. So I'm trying to figure out if I can get, maybe one of you guys or all of you guys added in as guests. I know there's a way to do this. Let's see. What was that? Just a minute. So get now what ninja, yeah, video ninja. Let's try this. We'll just call it what, and NXP meet, well, whatever. Let's just go with this 2022 December. This is stupid. Why would I put password over here? Okay. Then all right. Copy link. Yeah, I think this should work. Join this link. Right? You guys join? Not yet. Well, technically this should have popped up here. Okay, I think this is going to take a long time, but anyway, right. Did anyone join this link? Because if you did, I should be able to see you guys, yeah. Yes, no, maybe. Okay. All right. I think this is taking too long. I'm just going to get started. So yeah, our goal for today is we are basically going to go and we're going to try and do something like this. We're basically going to try and port we're basically going to try and get rustBoot working on the NXP i.MX8 board that I have here, which sort of looks something like this. Let me see if I can see it. Yeah, it looks like this. Right. Yeah, it's the NXP board. This is okay, I can't zoom into it, huh? But, okay, I've got this, wait. Yeah, this is the leaflet. So I hope you can see this. It's the i.MX8 Nano. This one's actually doesn't have the low power memory, the LP low power memory chip. It doesn't have that. It has the traditional DDR4. So I just figured out that there's a slight difference because of that. We'll have to take that into account. And then NXP has this thing called the advanced high assurance boot. I should probably have a link here somewhere, because I was just looking at all of this and there's a ton of information available here. It's hilarious, the amount of information that's out there. But basically, to start off, I would say that we can start off with NXP's main reference manual. The NXP reference manual is right here. I hope you guys can see this. It's quite exhaustive, it's thorough, etc. So we've got this. We'll take a look at this because that's important. But before we jump into anything, let's actually talk about the overarching flow of how NXP's secure boot works. So if I was to sort of look at that, I did save it somewhere. Let me see where it is. Yeah, so this is the simple, couple of lines description of what you need to do to get secure boot working. So I got a bunch of links over there for this. But what was I looking for? Okay. Yeah, I think I see Anand's up here. I think Anand's joined. But anyway, I'm not going to add the guest, Anand, because it's just taking too much time. I have to figure this out beforehand. So I'll just leave that be. I'll go ahead and just, continue without that for now. Yeah. So what was I saying? I was actually looking for yeah, the secure boot architecture. So let's look at that. Where did I put it? Let me just go find it. Okay. So just a minute. Damn, where did I put it, man? Advanced assurance boot. Yeah, this is the one I was looking for. Damn it. Okay. Okay, where are you? Alright, I think everybody can see this. So let me just blow this up a little more, just in case you can't see it. Okay, so this is kind of what it looks like. This particular chipset contains not one, not two, but actually contains, at least according to this high-level overview, it has 4 different cores. One is the cortex-a core, which is for the application processor. Then there's a cortex-M4 that you get to use. So these are the 2 cores that we get to use. We get to program, we get to, write stuff for. And then there is the SCU, and there's the SECO, they call it, which is basically, as far as I can tell, these are nothing but they're microcontrollers again. They're probably M4s, cortex-M4 chips, but they specifically run some NXP related firmware. So security controller for sure is, there's no customization, there's nothing that you can change as far as I can tell. Security controller is some proprietary piece of firmware that you get from NXP, and you just burn it onto you just flash it onto the controller, and that's it. SCU, on the other hand, there is a little bit of customization, or rather configuration possible, to the proprietary firmware that's provided. It's still NXP firmware, but you can just configure it if you want a bunch of different options, maybe. But just looking at this diagram, you can tell that this entire flow of things is such that you have the system control unit or system controller. It sort of is the first piece of firmware that's it's not the first piece of firmware, but it starts running. Then in tandem with the security controller, it works together, and then they end up you can say they end up turning on M4 and the cortex-a chip. That's sort of what we can tell just by looking at this diagram. right? So that's the overarching theme. How do you go about setting up secure boot on an i.MX8 chip? You sort of look at this, which is this particular picture, sort of gives you an idea. So you load some SU firmware, you load some CCO firmware into both these controllers, and then they run through initially a couple of things, and then control is handed over to the M4 and the application processor. See these two red lines that you see over here? That's what they mean. Now, our goal is primarily what in this entire thing? We don't, obviously we have nothing to do with these two cores, because that's anyway going to be running proprietary NXP firmware. So this is, this chip is what we're interested in, or this particular core is what we're interested in. As if you see, there's ATF, which is nothing but ARM trusted firmware, and then there's U-boot. So U-boot and ARM trusted firmware are two binaries that get to run. Or in other words, according to this workflow, you see that so when you have your cortex-a chip running, according to this, you see that ARM trusted firmware gets to run first, and then that loads U-boot. All right, something like that. So in our case, what we need to do is, at whichever stage U-boot is running, we'd effectively like to replace that with rustBoot, right? That's ideally what we're looking for. Now, with all of these pieces in mind, of course, I don't think today we'll get to actually touch a lot of code and stuff, because if you just look at this diagram, there's so much going on over here. We need to really understand each piece before we get to writing some code. But we'll anyway look at how it's been done on the Raspberry Pi 4, and how much of it can we directly just port over to the NXP chip. Let's look at those two things. Okay, so quick check. So far so good, making sense. Yeah. Okay. So I'll be pausing in between for questions. If there are any, maybe like a 10-minute break, we can, every 10 minutes I'll sort of look at the chat for any questions. Of course, I can't hear you guys. Sorry, I can't see you guys because this is a live stream. We're just testing this out. Let's see how it works. Okay, so keep this sort of rough picture in your mind. We'll get to the relevant pieces. So then what I started looking for is, now that this is what we need to, this is what we're dealing with. Then we need to go start looking at, okay, these other pieces. Now there must be some documentation around bringing up the board. Otherwise, NXP would have pretty much no customers, because without actual documentation, we can't expect the user to simply go ahead and figure things out. So we can start looking around, and I just sort of put some of these documents together, because I was actually searching for this morning, and I literally didn't have a lot of time, so I started looking at this morning, and I realized that there's a whole bunch of reference manuals, programmer guides, etc. available. And the one thing that's very common is that all of them together seem to be confusing the hell out of you, because the board that we're working on has a specific numbering scheme, and that board has a bunch of things that need to be addressed or need to be configured if you're going to get the right binaries produced, if you're going to produce the right binaries. So that being the case, I had to keep jumping from manual to manual to manual to figure out whether I'm doing things right or wrong. Okay, so with all that said and done, let's just sort of get to the main meat of the part. So there are two parts that I wanted to cover today. One is, let's look at the secure boot aspect of NXP's what we call advanced high assurance boot. And the second piece that we will look at is the implementation. That means what we've done on the Raspberry Pi 4. How do we sort of use whatever we've built so far, or rather reuse that in our port for the NXP chip, right? So let me just quickly switch. Okay, so I hope this should be visible, if I'm correct. The text should be visible. Yeah, I think it is. Okay, so this is, this is a document that's available by U-Boot actually. So the U-Boot project, because it's the de facto bootloader that pretty much all these, all of them use. That's NXP, RNSRs, TI, a lot of them. And they contribute to, so U-Boot's development and the Linux kernel's developments are very much I wouldn't say in sync, but they're very much alike. All right. It's not just the people that sort of contribute to the same two projects, but the kind of investment from different places. You talk about the companies that are sort of invested in Linux also sort of invest in U-Boot, because that's been going on for a while. But anyway, that's just a side note. So let's look at this. Let's start with this. So you saw the rough picture of what the NXP chipset looks like. Let's look at the secure boot process in a much more very focused manner, because there's a lot of information available saying you gotta look at these registers, you gotta pick up these configs, you gotta sort of pull in these proprietary binaries, etc. So all that's just going to be a lot of to wade through, a lot of stuff to wade through. Maybe we can use the U-Boot implementations as a starting point for us. All right, and that makes sense. By the way, U-Boot is not the only one. You have things like bareboot, which also is a fork of U-Boot, but now it's sort of evolved to a point where it's its own thing. So there's a bunch of different bootloaders that have support for the NXP i.MX8 series of chips. We'll be taking a look at what U-Boot has done, and let's see what we can take out of it and sort of put it in our implementation. All right. Okay, so I'll just pause. Up. I assume that makes sense, right? Okay. So this document, when you actually sort of put this together, you saw that there is a SECO, which is the security controller. You saw that there's the SCU, which is the system controller. And then there's the cortex-M4 and the cortex-a. These are chips. So that's effectively what this document says. When you're preparing a bootable image that will get loaded onto the final board here, which is this board, that'll get loaded onto this board. We basically need to get all of these things together. So you can see here, you'll need something called the i.MX make image tool. That's called MK image, which is basically a tool that's written by NXP itself. Now, that tool is very interesting because it does some of the same things that we've put together in the form of rustBoot utilities. Think about header generation, header construction, parsing, signature generation, all of that. Basically constructing a bootable image that you can basically flash onto your boards, right? That's the i.MX make image. SECO firmware is what we just talked about. It's proprietary firmware. We have no source code for it. We just get the binary. We go ahead and load it in. Then U-Boot. U-Boot is basically the bootloader that we are trying to replace. So U-Boot is what this document is written for U-Boot by U-Boot folks. So here we need to download U-Boot and build it. And then there's ARM trusted firmware, which is now, so this has nothing to do with NXP per se. Okay, NXP, pretty much any cortex-a chip that's they're using the V8 architecture, the ARM V8 architecture. Any ARM processor using the ARM V8 architecture pretty much requires ARM trusted firmware to be running so that you can provide things like secure execution, etc. So we talked about this where we looked at things like secure execution environments, etc. So ARM trusted firmware is a reference implementation from ARM itself that anybody can use. It's an open source project again, to be, basically used to sort of set up these secure execution environments within a cortex-a chip, right? So that's ARM trusted firmware, which is line number 29, right? And then you have system controller firmware. System controller firmware is basically what you just saw. There's an SCU chip as well. You would like to go ahead and put some firmware on it so that it does a lot of different things, which I don't think it's necessary for us to know, but it's interesting to sort of figure it out. So that's the SCU. And then there's the kernel as well. So as far as we are concerned, when we're talking about support for rustBoot, we'd like rustBoot to essentially replace U-boot and then boot this kernel image, which is probably going to be signed along with a root file system. All right. So those are the things that you need to be aware of. And then we need this code signing tool, which is again something very similar to what we've written for rustBoot. We have our own code signing tool, which will generate a signed fit image, which is what we need technically. That's something that we can reuse, definitely, because it's just, just need a signed fit image. We can do that. Now, so the way we're going to go about this is, if you look at this, it says preparing U-boot to support AHAB secure boot features. So a couple of things is, you will find something like this. Let me show you what a typical implementation looks like. This is ours. Yeah. Okay. So I've got everything over here. I've got the signing tools from NXP, which is basically a package called CST 3.3.1. I think there's maybe a more recent version, but I didn't bother downloading that because it has the OS X, the OS X version of executables for my operating system, which is OS X. And then it's also got ARM trusted firmware. I just cloned the repo. I installed the i.MX8 image. By the way, is this visible? I hope you can see VS Code. Yeah. So can you see VS Code right now? We're trying to port. So Anand's asking, are we trying to port U-boot for the i.MX port? No, U-boot's already there. We are trying to port, basically try to figure out NXP's boot process, specifically the secure boot process for NXP, and sort of replace U-boot in that flow. All right. We'd like to replace U-boot with our own bootloader, which is rustBoot, sorry. Okay, so I'm getting conflicting answers. Lavanya says yes, we can see VS Code. Anand says no, not VS Code. We can see browser, not VS Code. Okay, let me try this again. Okay. All right, so we just get started. Okay, I was talking to you guys about the prerequisites when you want to actually boot something like U-boot. When you want to get AHAB working on the NXP i.MX8 series of chips, you need to go ahead and pull in a lot of proprietary firmware. You need to pull in some build tools, some signing tools, etc. And you've got to put all of that together and then you finally get a binary which you can then flash onto your board, and hopefully everything goes well. You get exactly what you intended, which is maybe some print statements or some serial terminal output. Okay, now what I wanted to show you over here is all of the stuff that you saw in this document that we were talking about. All of these pieces, I've got them pulled in over here. Okay, so that's the first step that I would do by reading this documentation. I pull in all the prerequisites. Okay, that's preparing your build environment. And then the other part that I noticed is building some of this stuff actually has some nuance to it, because obviously we've never dealt with U-boot before. So if you want to build U-boot, there's a bunch of things that you need to do. One is we can go ahead and look at U-boot's documentation, which is somewhere here. Yeah. So if I go to U-boot's documentation, you will see that I can obtain the source. Yeah, this itself was a sort of a revelation, because U-boot and most of these older or really old projects don't use GitHub as their primary source. They have their own, some of them have their own, sources, or rather places where they store their own source code. One is, this is by Denks. I don't know what the backend is, etc. But anyway, it's different from GitHub itself. Usually people tend to use, or these older projects tend to use something called Code Aurora, which I've never heard of, but fine, I'm new. Okay. But anyway, so you can get the source from here, and then you can build U-boot, and there's instructions for it. Now, this is not going to go well, because this took me a while to actually get a build working. So basically what happens over here is, when you want to build U-boot, the reason I'm going into building U-boot, which is not necessary, but it's important, is because what we want to look at is when you put all of these different pieces together, and when the final binary is assembled, what does it really look like? All right. We want to look at those, we'll look at that format, or what we call that container that contains all of these different images that are baked into the final the final binary, right? So, and that's the reason we're looking at U-boot. Otherwise, we wouldn't look at it because we want to replace this. So what happens is there's a configuration file for every single board that supports U-boot, for which U-boots can be, for which you can use U-boot as the bootloader. So there's a configuration file. You need to go ahead and pull that out, and that configuration file has, for example, our configuration file is somewhere at the bottom. Yeah. Let me find it. Damn it. Okay. Okay, here we go. Yeah. Okay, it doesn't really matter. Let me just take one. So pick one. This is what you get. It's got a bunch of different config statements in there. These are like, you can call this conditional compilation, exactly what it is, where we are saying that I want you to build U-boot with these particular features turned on. Okay. So I want you to build me a U-boot bootloader for the ARM architecture with this particular counter frequency, with this particular system memory allocator length, and a whole bunch of other things. So you get the picture. You basically, your U-boot code base that's been written, you want it conditionally compiled, you want a bunch of different configuration parameters to be turned on. This is the file. So we first go ahead and make that file. Now this is where what I wanted to talk about when I said the stark difference between something like Rust using cargo versus building in a C environment using makefiles. So in the C world, you use makefiles and use the make tool to effectively build your, compile your projects, build your projects, and then sort of link them together and create, an executable, etc. And that's why it gets really gnarly, because I just spent time with this today morning, and I think I was, because I'm not used to this, I presume I would have ended up pulling my hair if I spent a little more time on this. Anyway, so you basically go ahead and pick the configuration file, you build it, or in other words, make it. And then that's after you've got your configuration file made, then you call make, which is going to do the actual compilation and produce a U-boot binary. The U-boot binary is going to be something like this, which of course you can't see it, but it's going to be something like this, all right? In fact, what I've done is I actually put everything in here just for my, sanity. So U-boot over here, when you actually compile U-boot, you get these two little binaries. We need these two. SPL is called secondary program loader. We'll talk about that, why that's important. That makes sense for us as well. And then there is also the ARM trusted firmware binary that's also going to be generated. Now, this naming convention might seem a little odd, BL31, etc. I'll talk about why that is the case. So yeah, so far so good, right? So we know what the what the high level overview is of how the NXP chipset works, which you just saw looked something like this. And then we looked at where is that? Yeah, we looked at the prerequisites, which are these. You need all these little tools to sort of build it. And then when you're going to build something like U-boot, you need to set some configurations, etc. in the def config configuration file, just so that you can turn on the relevant features that you want. All right. And as you can see, one of the important things in the configuration file that we need to turn on is config AHAB boot. This is important for us to go ahead and actually turn on a advanced high assurance boot. Now, this is the other important piece, because this is going to become important for us, because when I kept saying that the final binary is we need to know what it looks like. It actually looks like this. All right. So when we put all of these various pieces together, we package them in and we have a final bootable binary. It's going to have a header, which is called the container header. You can just call it a header, and a signature. And then you have a second container and a header and a signature. And then you have different pieces of firmware. You have the CICO and the SU firmware. Then you have the images for the M4 and the cortex-a chip. All right. So when you actually go ahead and put everything together, which is actually which takes quite some time to get it right. But anyway, I went through the entire process just to see how it works, so that we're not missing out on anything in a place where we end up down this path and we don't know a couple of things, and we somewhere down the road hit a roadblock. In order to avoid that, I went ahead and compiled the entire flow. I'm not going to talk about that entire flow because it was just me looking up a bunch of different places and figuring out how do you compile and how do you build and how do you package stuff. So that's not very important. But for for our sake, the important piece is this particular image format. So you will probably have something like this. All right, when you're going to turn on secure boot on the NXP series of chips. All right, so let's take a quick pause. Any questions so far? All right, let's go. So it talks about a bunch of different things that we just saw. Now, the other piece that we also need to look at is what does this header look like? Because if you remember, rustBoot has its own header. Now, we have two different kinds of headers. One is we use if you talk about microcontroller images, we have the rustBoot header. But if you talk about our Linux support, we basically use the fit image format, which is what even U-boot used. In fact, U-boot sort of came up with the fit image format for the U-boot project. So we use that just so that we don't have to worry about it at a later point, which is obviously right now. All right. So there's the header sort of looks like this. You'll have the header on top, then you will have the signature block, which contains all of the different pieces that are going to be included in the signature. All right, so I will sort of show you how this is entirely created, etc. But without going into all of these details, let's look at the basics, because what I wanted to cover was wanted to talk about secure boot in NXP, at least the basics. What is the high level overview of how do you go about doing things? And B, I also wanted to show you how we can do the porting of U-boot to rustBoot. Because I think we've already done most of the work when we ported stuff over to the Raspberry Pi, which is very much similar. Okay. So any questions on this part? Because I'm going to move out of this part right now. There's a whole bunch of things. These are all very specific when you actually get down to doing it, which I'm not doing it right now. We'll do it in a separate stream maybe. I just wanted to set up context and also learn how this live streaming thing works. So we thought we'll do this. Yes? Any questions? I somehow sense there's a delay, possibly. Yeah, but I don't know if that's in seconds or in minutes. Okay. So Lavanya has answered. So I'm guessing that's about a 10-second delay. All right. Okay. All right. So this sort of makes sense. Good. Now let's look at how so if we go back to this picture, what do we see? We see that U-boot pretty much runs on the cortex-a chip, right? So so far rustBoot support that we've built support for the the cortex-m series of processors, right? The M0s, the M3s, the M4s, the M7s, all of that. We support all of them. rustBoot supports, all of them, right? Cortex-A is something that is a little different in terms of the boot flow, etc. And we haven't actually built one for a production chip. We've built it for the Raspberry Pi, which is actually enough. It turns out it's enough. We could go ahead and use that to build our port for the NXP board, right? So yes, let me get to that part. All right. Okay. So I'll just sort of close all of this because I'm going to go through that, all of them anyway. All right. So yeah, if we go into boards, we'll find a folder for bootloaders where all of our bootloaders are present. That means each project or each individual folder is a bootable bootloader, which, as we know, you can simply go ahead and read the rustBoot documentation that's available here, which is here. and you can boot. And I don't know why it's in, yeah, actually it should be in dark mode, but fine, we'll start with this right now. So you can, there's documentation for pretty much all the chips that we support, and pretty much any Cortex-M series board, I think it just works because we've tested it and it sort of works. So, but for Cortex-A series of chips, it's slightly different. We want to figure out what's going on over here. So as you can see, we've built one for the Raspberry Pi 4, which is available. If you go into source, you'll find there's a main file, which is pretty much where our bootloader is written. So I'm going to step through this particular implementation because this is what we're going to use to port, to port U-boot, or rather to port the entire AHAB over to using rustBoot, or advanced high assurance boot, using rustBoot rather than U-boot, right? Okay, so what happens over here is, let's get quickly started over here. You see that, so there may be new folks watching the stream, but so I'll just quickly explain, what's in a Rust project. So you've got the cargo.toml file where you declare your dependencies. Much like, if you're writing JavaScript, you've got .json, you've got some JSON package manager. You declare your dependencies and you say, this is my package and I depend on all of these other things. That's what the toml file is. And then we also have this .cargo folder over here, which is what tells us, I'm going to be compiling. So I'm running this particular code is being written on the, a different machine with a different architecture. In this is the case, the Apple Silicon architecture. You could be writing this on something like Intel x86 or, a normal ARM machine, etc. So we need to specifically sort of provide a build target to Cargo, which is the package manager for Rust, to saying that, I would like you to compile this project for this target using these build parameters, or, compiler, linker parameters, etc. All right. Now with that out of the way, let's look at how this bootloader boots up on something like the Raspberry Pi 4. Similarly, in the Raspberry Pi 4, there's one piece that I missed that I did not talk about, and I think I should talk about it, which is why I'm going to talk about it. So we talked about this particular image. We saw that this is great, but I mentioned that, the system controller, the firmware that's running on the system controller is not the one that gets to execute first. That is actually, that is the domain of what's called the ROM, the read-only memory, or rather, in other words, the bootROM. And system controller is not the bootROM, as you can tell, because we are sort of flashing it. Although it's proprietary firmware, it's not the bootROM. The bootROM is immutable. It's burnt into the SoC when you get it out of the package from the factory. It can never be changed. That's the whole point of a bootROM. So I think there is a picture of it here somewhere. Okay, we'll just take this. This is good enough. Yeah, I hope you can see these. It's good. Right, so the ROM code is separate. You have a ROM chip that's present on the NXP board that contains this piece of code that's basically immutable. That means you cannot change it anymore. Not the manufacturer, not the, not the vendor, not the OEM, nobody can change it. It's burnt in, it's permanent. If you were to try to do something, you just basically have to go to break your board. That's what the ROM code is. It is what happens is this particular ROM code, or rather the hardware contains a one-time programmable piece of memory where you feed, you write some data to it. That data is basically a hash value. you basically write a hash value into some one-time programmable piece of hardware that the ROM code has access to. So the ROM code that's running in the ROM has access to this one-time programmable chip. So we go ahead and basically put a hash value in there. I'll tell you what that hash value is. So what happens in AHAB or in advanced high assurance boot is we go ahead and first we create a pair of keys. Actually, let me show you that because I sort of saved that as well. Where is that? Can you see my note-taking app? Yeah. Can you see it now? Okay. All right. So while I was sort of messing around with all of this, getting everything, preparing the build environment for it, I spent some time looking at how, what the theory behind it, how does it actually work, and in practice, how does it actually work. So I downloaded the code signing tool. As I said, there's a code signing tool. You've got a script in there that allows you to create these keys and create what's called the hash value that I talked about. It's actually called a fuse binary that you can fuse or rather flash onto the one-time programmable memory that you have. Okay, so basically what you do is you generate what's called a basic PKI tree. The PKI tree is nothing but you generate one root or rather okay, they've sort of messed up the names. So you generate one CA. A CA key is nothing but your source of truth keys. Okay, it's the first pair of keys, which is like the master pair of keys. All right, because those keys are going to be used to sign everything else below it. All right, so you generate what's called the CA keys, as you can see here, and then you generate what's called the SRK keys. SRK are called super root keys. Now that's why I mentioned the naming is a little messed up, because the CA key and there's a super root key sort of gets confusing. But anyway, so what happens here is I basically, when I run this script, it's going to generate, you do nothing, you don't provide any input, you just run the script. All you need to have is you need to have OpenSSL installed on your machine. When you have OpenSSL, the tool, which is it's a utility that accompanies OpenSSL library, the installation. so that you can actually do a lot of things. You can generate keys, you can test your hash functions, you can create certificates. A lot of these things can be done with OpenSSL. So that's pretty much what you need installed on your machine, and you run this script, you will get this output. All right. In this output, one of the important things is, you see that we're generating the CA key, we are generating the SRK1, SRK2, SRK3, and SRK4, right? So what this is actually doing is, you do provide some input in the form of an interactive text prompt. You say, you basically answer these questions. But here I'm using ECC, the elliptic curve cryptography. So I'm using the curve P256. So I mentioned all these things. I mentioned that I'm using a SHA-256 hash. I'm using the the P256 curve, and then a bunch of other options. Anyway, it generates the CA. It generates the CA keys and certificate. It generates the SRK keys and the certificate, 4 of them. The SRK keys and certificates, 4 of them are generated. Okay. Now, once that is generated, what I did is I basically pulled in one of those SRK keys, and I said, okay, let me just look at what's inside it. As you can tell, it's a key. So it's a 256-bit key. So in this case, you can see that you'll have the 32-byte key, and then you will have your public key, which is 64 bytes, right? So both of them are there. That's it. Now, the other piece is you have OpenSSL. Sorry, that I just took a look at what's inside the key file, and you see this. And then I took a look inside the certificate. You're generating a key and the certificate file. So what's actually the certificate file? You see that this certificate file is a very basic one. It's not like the ones that you see on your websites, etc. Very basic, but it's an X509 certificate. So the important thing over here is the public key. If you can tell, it's the same over here. So I'm basically creating a certificate for this public key, for the owner of this public key, and with my signature. Who is that? Who's creating this? That's the CA key that's doing this, right? So just pause over here. I hope that makes sense. Okay, sorry. Is this visible now? I think Lavanya mentioned it's not visible. The font size, is it good for my editor? Okay, I presume this is working, so I'm just going to go forward. So that's the idea. So you have the CA certificate and a key that is being used to actually sign these SRK certs, or rather issue SRK certs, signing the public key for the SRKs, right? So that's the relationship between the CA and the SRKs. And then then what is it that's actually flashed onto the hardware? In the NXP board, I said that there's a one-time programmable chip. What do you actually flash onto it? You actually flash this thing called the fuse.bin file. What is the fuse.bin file? It's nothing but a collect. You don't actually concatenate you sort of take all these 4 different SRK keys, you combine them, you add a little bit of header in front of them, and then you combine all 4 of them, and then you run it through a SHA-512 hash. And then you get 64 bytes from it. And that entire thing is done by this tool called the SRK tool, which is part of the signing tools. So that's kind of what I've shown over here. The SRK tool takes in, it takes in the table.bin. Table.bin is all the concatenation of all the public keys. Then it also takes, you're providing it a name for where you should put in the final result. And then you provide all the different certificates. So you take all of this, and then you create your 64-byte hash value that goes into the one-time programmable memory of pretty much any chip. That is your trust anchor. All right. So in the earlier diagram, you saw that this ROM code actually relies on a SRK hash table or a value. That value is also immutable. It's baked into that one-time programmable area, and that is only accessible by the ROM code. So effectively, the ROM code says, okay, I only trust this particular value. So any other private key that's going to be signing any piece of firmware, I'm finally going to do the hashing and check whether it's equal to this value. All right. So the public key value that I get, which I'm going to be using to verify a signed firmware, I'm basically going to compare the hash of that public key with whatever's in here. If they match, then I can be assured that it was signed by, the right private key, or the private key that I trust. Right? Does that make sense? I hope that makes sense, right? Yeah. Okay. I guess I've got to get used to this time delay when streaming. Okay, so that's good. So I just wanted to cover that because that makes sense. Why are we doing all of this? So there is something like a ROM right before this. There is the ROM, and the ROM has access to the one-time programmable memory, which contains the hash value. The hash value is actually generated using that process that I just showed you. And then whenever you sign firmware, for that you'd want distributed to your particular device, it must come from the key that signed that. The private key that was used to sign must be the same as the one that's been baked into the one-time programmable fuse. Right? Okay. So far so good. So I hope that sort of makes sense. Let's just take a quick pause and check for any last questions, and then we finally move on to the implementation phase. And hopefully I don't have to do a lot of editing over here. Yeah, guys, anyone? I'm sorry, I have to keep asking because my phone's sort of capturing my video, and this is the only way I can communicate. Interesting. Okay. All right. So Anand says, yes, we can move ahead. Let's move ahead. All right. So now we're in the implementation. All right. We looked at all of that. It's a good starting point. We've not yet come to the point where we see, okay, how do we actually, replace rustBoot with U-boot? So the point that I mentioned was, finally, when you actually compile uboot, it gets to run on a cortex-a chip. That's the important piece. So if you had any other implementation that you've already built that runs on a cortex-a chip, then most likely you can just reuse that. Specifically an ARM v8 chip. And that's exactly what we've done. That's why I wrote the Raspberry Pi 4 bootloader. Of course, most of it was something that's community sourced by an excellent project called the Raspberry Pi Tutorials, which I will also showcase because Andre Richter is just awesome. So he helped me out quite a bit. So I wanted to shout out to this particular project because this project sort of, I didn't have to read the entire ARM manual because a lot of it was made very, very simple and very easy to understand. And effectively, the amount of time that you'd have spent trying to figure everything out reduced from, let's say, a couple of weeks to maybe just 2-3 days. And I highly recommend this project because this project walks you through building bare metal software for the Raspberry Pi 4 and 3 using Rust. And since we are writing Rust and rustBoot, obviously, I sort of used most of this as is and then added the pieces that I needed, like the flash drivers for the chip, because they didn't exist. In this case, they were just using a UART loader or a chain loader, etc., which doesn't work for us. We wanted to actually build a flash driver for the Raspberry Pi, and we did that. And then there's a bunch of pieces that we've actually put in as well, which is things like support for a file system, support for the FAT32 file system, support for the device tree blob. All of those things have been built there because we want to actually support booting Linux. So yeah, so just keep that in your mind. We started off with a base using that, and we've come all the way here. Okay, so if we see here, we've got the main file, and in the main file we see that we're pulling in some of our implementations that I said, which is we wrote a BSP which contains things like the flash drivers, as I mentioned, things like the drivers, etc. So I pull in that, then I pull in my FAT32 implementation. The FAT32 implementation, I had to pick one implementation. It's good, but I have a few questions about it. It's called the embedded STM-MCRS. It's good. It's just that I had to do quite a few additions for my use case. We'll talk more about that if we have a little more time. And then we also pull in some extra helpers which are in the boot and the fit. So this boot and fit that you see that I've included, this is all stuff that's just, you can think of them as utility modules that we need. Okay. Anyway, so once we pull in all of this, the important thing that we definitely need is, there's no way to figure out what's going on other than to actually get some debugging information. The way to do that is to get your UART working first. So my initial goal was always, when I started off, is just write enough code so that you have a GPIO pin, you have your GPIO pins running, and you have your UART running, so that you get some debuggable output, right? So I got that working first. Now, before I jump in to kernel main, let's actually take a look at where does execution begin. All right. So execution actually starts in this boot.s file. This is the starting point for our bootloader. All right. And without going into the details of everything, because there is documentation available again over here. If you go to, we have good documentation available over here. I talk about, all of the different pieces, like how the Raspberry Pi 4 boots, etc. So that's mentioned here. It's very weird, but it is what it is. So effectively, you can think of it this way. All of the boards out there that have a cortex-a chip on them, they may have really wonky initial booting logic. That is logic that stays, that's sort of fixed. It's immutable. You start from the bootROM, whatever starts in the bootROM, and then you jump through a bunch of different chains, etc. All of that is all the vendor-specific code can get as crazy as they want, because they want to do a whole bunch of things. In Raspberry Pi's case, you can see that when you supply power to the board, you don't have the cortex-a chip running. You have the GPU running first for some reason. Well, okay, fine. After it's powered on, you actually have a bootROM running, which contains the first stage bootloader, and then as I mentioned over here, the GPU contains a tiny RISC core, which means it contains another core that contains the bootROM. So your actual main application processor is not even activated to this point when you actually turn on your processor. The bootROM gets to run, then it loads the second stage bootloader, then you mess around with the fact that you don't have access to your main memory, because it's not even, the chip is not even initialized. You need to figure out, how do I get that running? So there's a bunch of different memories available for loading and running this type of code. All of that stuff happens. But at the end of the day, after that entire flow, after that entire vendor-specific flow, you get to a point where you have access to your cortex-a chip. All right, and there you can get to run your code. The first user-supplied bootloader, you can say. All right, and that's exactly what's happening here as well. Where if you go back here, that's exactly what's happening here. Once that entire vendor-specific boot flow is complete, it hands over control to your bootloader. Right? So, and when we the way you can think about this is, when you create the link file, the linker script, pretty much the bootROM or the piece of code that runs prior to your bootloader in the Raspberry Pi 4's case is supposed to be loaded at this particular value. The physical address at which the binary is supposed to be loaded is this value, so that it'll just pick it up and just pass control to that location. Now, given that is the requirement, what we do is we write an assembly file. That's why it's a .s file, and then we do a couple of things over here. In the assembly file, I say this is my start section, and this I've nicely commented this, so it's very easy to sort of go through this. So when you start up the Raspberry Pi at this stage, it is executing at something called an EL2 stage. We'll talk about these things. These is nothing but EL2 is nothing but exception level. So exceptions are something that exist in pretty much any processor. You will see that there will be exceptions of all kinds. There will be synchronous, there will be asynchronous, which are called interrupts. And there will also be, in those asynchronous interrupts, you'll have many different variations. But basically synchronous and asynchronous exceptions are what you get. Exceptions are nothing but something went wrong, you need to handle it before you can move on. All right. So EL2, the processor can have multiple exception levels, in the sense that the exception levels are actually privileged. So EL3 is higher privilege than EL2, than EL1. I don't know if there's an EL0, but fine. You get the picture. It's basically a hierarchy of exception levels that the processor can be in, saying that if the processor is in EL2, then only EL2 code that's running can do a bunch of things. You can't have code that is supposed to be running in EL1 making EL2 requests, right? So at each level, you have certain privileges. You can get to do something. So if you have code running in EL1 and tries to do an EL2 operation, you're obviously going to get an exception. All right. Yeah, that makes sense. Okay, I'll just move on. So we go ahead and check to see whether we are executing in EL2, because we have to do that check according to the ARM manual as well. And then we proceed depending on that check, whether or not we move forward or we jump to what's called a parking loop. That means this is the parking loop, right? All right, so see, some of you might not know how assembly actually is written. I didn't know either just a couple of months ago, but now I do. So assembly is basically, when you're writing assembly, this is what it looks like. You write your function name, you can say, it looks like this. And then the body of your function in here, the basic assembly instructions are written in this manner. Likewise, same thing over here, same thing over here. Okay, I'm not going to get into what this .l and all mean. That, I guess, we can look at it later when we actually sort of talk about assembly programming, because quite frankly, even I need to sort of check up on a bunch of different things. But anyway, and a .equ basically means equals. It's basically trying to say that this value or this variable equals this value, and this variable equals this value. So that's just, and then you can also write macros. Here's how you write macros. Macros, as you know, are basically your code that can be expanded into actual assembly. So much like what you would see in any other language, you can write a Rust macro, but it doesn't look like Rust at all. But it can, when you actually expand it, or when the compiler, during the compilation process, when you expand the macro, you will see that it generates real Rust code. Some people in the community just refer to it as code gen, just so that you know, because it can be confusing. I was wondering what code gen was for a very long time. Okay, just so that you know. All right, so we check the exception level of the current core, and if it's not what you call at a certain exception, if it's not at the EL2 exception level, we simply just go ahead and park. We don't go forward. We just go into that parking loop. That's why it's called a parking loop. All right. Now, and then here, what we do here is, if we are running at EL2, which is exactly where we should be, then we will only turn on the boot core. That means, unlike your microcontroller chips that you've so far dealt with, they're single core. All of them are single core mostly. Of course, if you can have a dual core cortex-M chip, that's different, but you'll have mostly a single core. But when you talk about application processors, there are more than one cores. That's the whole idea of this quad-core, multi-core, method. For our case, we just need one core, all right? Because it's just a bootloader, specifically with rustBoot's requirements, where we want the trusted computing base to be as small as possible, and we want as little code as possible in the bootloader. We just need the one core to get started. So we turn on just one core, and that's what I mentioned over here when I said core ID, which means which core do I want to turn on. So I basically want to turn on core 0 in this case, which is what this is. Okay, once that's done, we will go ahead and then we're just turning on one core. If we fail at doing that, we will simply stop. Okay, again, we'll jump back to the parking loop. If we have succeeded in turning on the single boot core, then we jump to the initialization portion over here. All right, so here what happens is, in the NXP case, I mentioned that there's a very important thing that you need to keep in mind, which is there's memory that needs to be initialized, etc. In the Raspberry Pi case, I didn't need to do much because everything was already set up before before the rustBoot controller got access to the, to the system, or got control of the cortex-a chip. The DRAM, which is a separate chip, which is the system memory chip. So the system memory is actually a separate chip. It needs to be initialized. That's already been done in the Raspberry Pi's case, so I didn't have to do much. So I just have to go ahead and sort of zero out the BSS section, which I do, which is pretty much what happens over here. Okay. Now, okay, I'm not going to go into exactly. This is a little different because these are some symbols, or you can think of some variables that we get to use in our code later on. You'll see why. But anyway, we zero out this particular region of memory because we want to use this memory as our BSS section. And then here is where we end up jumping to the Rust code. This is prepare for Rust jump. So once we hit this point, that is line 67, we will be in Rust land. Okay. So I'll just take a pause here because in the interest of time, I'd like to wrap this up in the next 15 minutes. So yeah, questions, thoughts? Okay. All right. Yes, there are none. So let me move forward. So now that we've actually hit the point where we are saying, okay, we've done this little bit of assembly work because we've sort of set ourselves up for, set our bootloader up by going ahead and activating the only core that we need, ensuring that we are in exception level 2, zeroing out the BSS memory, and then we go ahead and jump into the Rust code. Now, where is this particular start? If you were to sort of look at it, so what happens is when you actually compile your program, the linker knows that, okay, start Rust is here. It's going to go ahead and jump to, the symbol named start Rust. And where is the symbol named start Rust? So it's in the boot.rs file. If you just scroll to the bottom, where is that? Yeah. All right. So this is the entry point for the Rust, the Rust land. So here, what we basically do is, again, because we ensured that our core is only our processor is only in the EL2 state to execute. To execute the kernel, we actually need to drop down to one level. Now that's, if you ask me why that is because the manual says so. We need to do that. And the way we do that is using, basically Rust. Here we can just use Rust and all the goodness of Rust because we get to use things like this, right? This is very descriptive, unlike this, where we actually had to figure out, okay, which register am I using? Where am I popping? Am I comparing? Am I, all those specific things? Instead of that, you get to write it in this way. And all of this stuff is compile time checked, right? So by the way, this register that you see comes from cortex-a, which is the crate that I'm using over here. So let's just look at that. Yeah, the cortex-a crate. We also have talk registers, which I use for other things as well. But in this case, you're using the registers over here. So these registers, the way this register is implemented in Rust is that when you actually set the bits, there's a lot of static checks that go on, or compile time checks that go on that avoid you from making mistakes. because we are using types to represent these registers in code, we can ensure that we cannot build types that are inaccurate for what we want, that is. Right? Okay. So this particular start rust method just jumps to, basically goes ahead and drops one level in terms of the exception level for the processor. And then we come down over here. We basically go ahead and set the exception level over here. So I don't want to get into this because this is just nothing but register setting. You're looking at something like the status program register, you're looking at the counter. A bunch of different registers need to be set so that we can ensure that we jump. The only important piece that I'd like to make is that the final register that you need to set is this SP, whatever this register is, the stack pointer, and the link register. If we set these two registers and then we basically call this instruction called erect, the core is basically going to take whatever's in the stack pointer and whatever's in the link register. It's going to push it onto the instruction pointer. Whatever's in the stack pointer, it's going to say that that's your stack. That's where the stack is. Okay. So pretty much that's how we jump to, we go ahead and, what do you say? Jump, or rather jump from EL2 to EL1, or transition from EL2 to EL1. And then we use this erect instructions to sort of return to exception level 1. All right. So we set up some of the code in EL2 to EL1 transition, and then to actually jump down to EL1, we need to go ahead and call this erect method. Okay. So what are we doing here basically when you call erect? You would notice that we don't know where you're actually jumping to, right? So the point that you need to understand here is this is where we're jumping to, right? So if you see this is the kernel init function that you will see in the main, file. This is where we jump to, all right? So from assembly, you sort of moved into Rust land. Then in Rust land, you do a little more setup. You jump, so you sort of drop down in exception level, and then you jump into your actual kernel code that you've written, right? So once you're here, you will see that I've got a bunch of things running over here. Now, the reason I wanted to spend some time over here, which I think we will do a longer stream about, is we'll actually go ahead and build this out, and we'll sort of do an end-to-end session, but probably a much shorter one because this is all over the place, I realize. So in here, when we see kernel init, we will see that in the initialization function, that's basically it. We're initializing our bootloader. And the reason I keep calling it kernel is because technically that's the name you want to use for, the bare metal piece of code that you're running. But yeah, it's just a name. We can go ahead and officially give it a name depending on when we write our documentation out fully. Okay, then here what we do is we basically initialize handling, exception handling. I have not talked about exception handling, which obviously we'll need more time to do that. But anyway, exception handling is initialized. As I said, exception handling is basically what you're saying is that, as you can see over here, when we are initializing exception handling, we are basically saying, we're basically setting the what we call the VBAR. It's called the vector base address register. When you set that, you know that, okay, if there is an exception that occurs, either synchronous or asynchronous, the hardware knows where to go and say, okay, how does this particular exception has occurred? So I'm going to go over here. This register is going to contain the address. I'm going to look up the interrupt vector table or the exception vector table. And then, I'm going to pick the exception vector handler or the exception handler from there and I do my thing, right? So that's sort of what setting up exception handling is. All right. If you remember in cortex-a, you didn't have to do this because you didn't write it though, but it's actually part of the hardware abstraction layer that's provided to you, right? Okay. And then you also set up the MMU. Now, I thought we could spend time on this today, but I guess it's going to be later, because an MMU is an important piece of a code that specifically when you're writing something for the cortex-a architecture, because you could technically go ahead and write code without exception handling setup and without MMU. Except without exception handling, you'll have a very tough time if there's any debugging output that you need and you don't have access to. You won't get it. MMU, like I found out, without that you can't do a lot of things, like your performance goes for a hit toss. You can't do things like unaligned accesses, which I will talk about. But anyway, that's why we need the MMU. But to sort of make things clear, you can go ahead and write a bootloader for the cortex-a chip without exception handling and MMU, as I have done. All right, you can go ahead and do that, except that yeah, you can actually, when you're writing out your bootloader, my advice is you start off without these, at least till you get your UART working. Now after that, then you can go ahead and turn these things on, because you'd want all the relevant pieces to also work, which is you want the performance, you want exception handling to work, etc. All right. Then once that is done, I will go ahead and enable all my drivers. I only have 3. I have what you call an SD card driver, which is called an SD-MMC driver. And then I've got my GPIO and my UART. That's it. Those are the drivers. rustBoot is going to be that bare bones. We'll just support that much. Something for the non-volatile storage, a UART, and GPIO pins to support the UART. And if there are crypto elements available, etc., as you will see, there's a CAM module in the NXP chip, which we will try and build support for, so that you get security event information, etc., that you may need. All right, so that's the initialization. So you initialize, you set up all of this stuff, and then you finally jump to your main function. In the main function, you do your thing. You already have control over the core. You have a single core running. You've enabled the MMU. You've enabled exception handling. You've set up your drivers. All of that is done. Then you go ahead and start running your kernel main, right? In your kernel main, you do everything. Like, for example, I go ahead and create my controller, and then start running my start running my start accessing the file system that I have support for, and then pull the kernel out of the file system, pull the DTP out of the file system, which is the device tree blob. So there are 3 things that I need to boot the Linux kernel, which you will see. Hopefully I can show you in one shot. Okay, yeah, you see there's a method called load fit, which is loading the fit image and verifying the authenticity. This fit image actually contains a couple of things. It contains the kernel that I want to boot, the Linux kernel, the device tree blob, and the root file system that I would like included. So those 3 things. Then once I load, the fit image, the fit image is actually signed. So I want to verify the authenticity of that. And then I do a bunch of relocations and, kernel DTP patching, etc. that needs to be done, which we will cover later. And then we're done. Once that is done, we go ahead and start the kernel, and we just jump into the MMU. Sorry, we disable the MMU and we jump into the loaded Linux kernel and pass the device tree blob as the argument to it. Okay, So I'll sort of show you what the output looks like. Hopefully I have some output here. Yes, I do. So yeah, this is what the output looks like. So when we basically sort of connect, our flash controller is turned on. It does a lot of different things, as you can see over here. We go ahead and turn on the MMU. You can see that the MMU is turned on. You see that we are executing at the privilege level EL1, which is what we've done. These are the different privilege, or you say exception types. System error, interrupts, debug is nothing but synchronous exceptions, and then the fast IQ, etc. And then I load my drivers. These are my drivers that I load. Of course, I've already loaded my i.MX8 or the flash driver, which is why I've not listed it over here. And then I am sort of accessing the FAT32 file system that I have support for in my bootloader. I access the device, the fit image, which is called an ITB blob here. And then I authenticate it. I check the signature out. Then I start loading the different pieces that are part of the fit image. And then I simply jump and the kernel takes over and I'm done, right? That's it. That's pretty much what happens on a cortex-a chip when you want to run the when you want to basically have a when you want to basically have a bootloader boot assigned fit image or assigned Linux kernel along with its additional things that it needs, right? Okay, so I'm gonna, because we've taken up quite some time, any questions? All right, guys. Okay, I don't think there are any other questions. So I hope this is a good start, at least. I think the next time we'll probably have, a couple of us as added in as well into the stream, so that, we can actually sort of have a multi-way communication that's live, and that should sort of help us. Okay. Yeah, the Raspberry Pi code is already committed. So Anand's asking, will you commit this code? Yes, this is already up. I've just gone through the same implementation because we're pretty much going to take the same implementation and adapt it for the NXP implementation. That is, when we write rustBoot for the NXP implementation, it's going to look like this, except there's going to be things like DRAM initialization, some interfacing with untrusted firmware is required, etc. So we add those little pieces in there, and then we get everything else working. Of course, we're going to need to see if the flash driver works. It should, because it is a standard flash driver. But yeah, there may be some register differences, etc. Maybe we need to sort of refactor that probably. So yeah, a little bit of work over there, but effectively the outline should remain the same. Yeah. Okay. That's it. I think we're bang on time, 1 p.m. I was expecting this to be much shorter, but yeah, I don't think that's ever going to happen. Okay. All right, guys. I don't think there are any other questions. So cool. That's it. See you guys. I'm gonna stop the recording for now.